Alright, this is the third video of my DE10-Standard tutorial series, and this time let's play with the HPS or hard processor system, and let's begin. So as I said before, last time we have the SoC chip, which has FPGA fabric and HPS core, and the HPS core is pretty much dual-core Cortex A9, and it boots from SD card. So from Terrasig website, they provided actually two different versions of the image. One is the one with the XDE desktop, and the other one is just console. In this case, we're going to use the console one. They are pretty much very similar in terms of kernel and a lot of things, but the XDE one has a graphics, has X window system, so you can run some graphical programs, and if you want to hook it up to a display, then that's your choice. And if you just want to do some basic things and talk with FPGA, do some headless things, then you probably want to use the console one. The main difference in terms of the low-level hardware is that the LXD one has a default device tree file, and the device tree will actually try to load image to the FPGA image to the FPGA during boot up, and also it will try to initialize a lot of the FPGA peripherals on the AXI bus, and the console version will leave the FPGA unconfigured, and also it won't try to access any of the FPGA peripherals. I mean the peripherals developed in the QCs and supposed to be in the FPGA when the kernel boots up, and it won't try to initialize any of them. So the reason I'm using the console version is because I also want to play with QCs to create my own HPS design. And in this case, a lot of the peripherals in their Terrasig's reference design won't be there. I will remove them, or I will just start a design from scratch and put my own IP blocks. So in that case, the graphical Linux, the DTB file will try to actually talk to some of the peripherals that's supposed to be in the FPGA, but since in my implementation, I don't really have these peripherals. And what happens is the kernel will crash, will panic, because it tries to talk with something at a particular address, but it cannot find that particular device. So in this case, I will use the console version. You download that and open that, you will see an image file. And you can use your Win32 disk imager for Windows. And for Linux, you can use DD and then choose the file. And it will be, I already extracted that. So for we have the standard desktop one and the console only one. I'm going to use this one. And I can just write that into a flash drive. In this case, it's just a memory card, which is going to go to this SD slot. I've already done that, and this is actually the flash card I just made. So before we boot up the board, we have to have a mechanism to talk to the board. So we have the USB serial port, and that will be the main interaction before we establish the network interface. And I'll talk about later why the serial port is so important, that it's more important than network. So let's go to PuTTY. We already made this connection, load it. You can see your port number from your device manager. You will see your ports, and now we have the FTDI adapter. Great. So we open the serial port, and let's power the board. So that's the U-boot. And see that we cannot read the FPGA configuration file, which is normal. In the console version, it pretty much just doesn't have the file. It has the file in the file system, but it's not at the correct position. It's actually designed to do so. So if you don't want to configure the FPGA, then the U-boot will not try to configure the FPGA. That's a design feature. And if you want to copy the file to the U-boot configuration partition, then you can also load the FPGA on boot up. That's up to you. That's your choice. So we log in, no password, And you want to customize the SD card because the SD image is actually designed based on a certain card size, maybe 2 GB or 4 GB or something. You want to expand the partition so that you can use all the entire space. So they are good enough to provide one of the scripts, expand. Okay. Oops, what happened? Oh, it should be fine. It should be done already. Let's reboot. And we are going to call another program to finish the resizing process. Let's see, starting kernel. It actually starts fairly quickly, fairly fast Linux. Yeah, there's another one, resize. And now we can reboot. Finished. And now we have a fresh installed Linux distribution on this card. Let's see what features the Linux provides, especially for the HPS. Let's see what we have. Let's first do some tests on the LEDs. Oops, we only have the HPS LED, as we know that this is the HPS LED, and we're supposed to have 10 FPGA LEDs. But in this case, we don't have any of them showing on screen. So what happened? Well, because Linux, as I said before, the console version doesn't try to configure FPGA and configure device tree, so the Linux kernel will know that there's a particular devices on the bus or something. It doesn't try to do that. So you have to do that manually, which is good for us if you're going to design QSys and you're going to do a lot of your custom cores. But if you want to use the just want to use the provided out-of-box HPS experience, then you have to load it. So how do we load that? Well, first let's mount our config fs -t config fs config fs, let's say a random place, cd to that place. Alright, and cd to let's see, device tree overlays, and let's create a new overlay name. Let's whatever name. Let's say test. And now we are going to load one of the DTB overlay into this file. And where is the file? Well, it's actually here. /firmware. You will see you have a device tree overlay, and you have the RBF is actually the configuration binary bit stream of the FPGA. And when you try to load this overlay, the overlay will have some information contains where you can find this file. So let's load this file. Let's echo the name fpga.dtbo to now we are in test path. Alright, let's hit enter. Now it configured the FPGA. Now we have the 7 segments, and we have the heartbeat, and we have the LEDs, and also switches, whatever things. They're all configured. And the exact configuration is determined by the DTBO and the RBF, which later we can generate the same file in QSys. So now, after we loaded the device tree, we can see a lot of new LED devices in the classes. Let's see. Now we have a lot of files, and these are the exposed different LEDs. So let's have let's try to turn on the LED2. Let's see what happens. Echo 1 FPGA let 1, let's say brightness. Now we can turn on this LED, and also we can use the same way to turn it off. So yeah, that is how do you load your FPGA bitstream and your device overlay. Now let's see if we can write a program. Let's say start from hello world. So there are two ways you can write programs. The first, TerraSync is kind enough to include GCC in their Linux distribution. So I can actually just run GCC from the console, which is great. So let's say hello.c. So now we have a hello world. Now let's GCC hello.c, and the architecture is SOC C. And hello. Now we have the first program written directly on the chip. However, sometimes you may want to write your program on your computer and copy the program to your HPS board. So how can you do that? Well, there is a tool called EDS. You have to install EDS when you install Quartus. So when you are installing Quartus, you are downloading the Quartus program and your device package and also the ARM EDS. You have to install all of them and to get this environment. So let's try to do the same thing on your computer. Okay. Let's create a folder called test, or let's just call it hello. Hello. All right, we can see that. And we can create our program. Hello.c, right? Same program. Alright, very simple program. Now we can compile it. Now you can use a make file, or you can just program from the command, compile from the command line. So just for the simplicity, I'll just do that from command line. GCC and hello.c. Oops. Oh. Alright. Now we can see the program. Of course, we cannot run the program because it's not compiled for x86. But we can just run the same program actually on the board. So as I said before, something is annoying, a very annoying difference between the LXD version and the console version. The console version actually has some problems when you're trying to SSH or SCP to the board. For whatever reason, it doesn't work. So let's see. Let's try to get an IP address. So actually we can do the DNS or something. You see that? We have an IP address. Google DNS works, so we have the network. However, if we try to SSH this computer, it won't work. 225. Oops. Hello? Yes? Oh, it works. Great. Great, 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 great. Oh, for the first time, for the few days, worked. Very, very great. Thank you very much. Thank you very much. Thank you very much. But of course, that's a safety hazard because we're exposing our service to the web, to the internet. So we have a router and net translation. So we have the private IP, but that's still not a good idea to expose your system without password. So let's say what if we add a password? See, let's add a random password. Okay, now we have the password. Now let's see if we can still log into the system. Oops, that's the problem. Whenever you have a password, the system will not allow you to log in. And if you don't have a password, actually this is the first time I try that without a password. So it works without a password, but if you set the password and it won't work. Even if I SSH to itself. Yes. And see that? Broken pipe. So that means the board best work without a password. Okay, I take the risk. And by the way, the kind of broken pipe issue actually not only exists in SSH, also exists in any of the SSH-based protocols like SCP, whatever things. So if you want to use WinSCP to drag and drop files, it won't work either. So you have to clear the password, I guess. Okay. How do I get rid of the password? How do I get rid of the password? Well, anyway, let's forget about the SCP thing anyway. I have another way to transfer files between the boards. So in this case, I actually, because I cannot connect to the to this board per se, but I can from this board connect to another computer. So let's run a virtual machine. Oops, I just ran the wrong computer. This is the virtual machine I used to do the Yocto development on IMX 6 ultra low power for one of my other projects, but I just decided to reuse the system for a general purpose Linux operating system on my computer. Let's log into my computer, Linux box, and there should be a shared folder between the host and the. Let's open that. It's gonna be here, source, and here's our program. Let's copy that. Okay, and now you should see that. Refresh that, and you can see that. Copy that over here. All right, we have the program. And let's see what's IP address of this computer. 222, okay. So all right. So this is the console from the board. Yes, the password. All right, and it works. So that's the two different workflows. You can compile the program on your computer or compile the program on the board. So that's basically how you work, set up the very, very bare minimum environment for your HPS development. And before I end this video, I want to say, if you want to do QCs, please use this image. Otherwise, we'll give you a lot. I don't really want to stress this so many times, but it's really, really important. It cost me a lot of time to debug why the kernel won't boot. Eventually, I realized there is something that's supposed to be there, but my custom image just doesn't have that. And by the way, if you want to, so right now we have the FPGA configured. So how do we reconfigure? So dynamic reconfigure the FPGA. How do we do that? Well, now we can see we have the test. If we remove the test, actually we can create a new, let's say another thing called test, and redo the process. So we can insert another image to the FPGA. So let's create another test. Path. So you will see the FPGA reconfigures. So that's the way you reconfigure FPGA without having to reboot the entire system. And in case you just want, you really want the FPGA to be actually automatically configured, the way you can do that is, let's first shut down the system. So system halted. Keep in mind that the FPGA blinking will still work because we're only shutting down the HPS, not shutting down the FPGA part. As long as it's configured, it will still work. Now we can remove the card and put that into a card reader. Let's see what we have. Now, you can see from the U-boot script, some binary things trying to load the FPGA, and then we have basic U-boot human readable script. It actually tries to load FPGA stream from this file, which we don't have over here. So that's the reason why the system will not load FPGA image from when it boots. And if you happen to have that file, let's say we generate, we design our QCs and we generate the FPGA bit stream, we can copy that file to this folder, and then whenever the system boots up, it will automatically load the FPGA image. So that's a small trick. But anyway, that's the end of this video, and see you next time. The next time we're going to talk about QCs, and we're going to implement a very, very basic system from scratch. So we're going to implement a QC system with a 8-bit LED, and then we'll implement a program on the HPS to control the LED. So see you guys next time. Thank you.